Welcome back for lesson 3, solubility equilibrium. So now we're going to be talking about the solubility aspect of equilibrium. Equilibrium is not just a one-directional option. Even with salt, sodium chloride, you put the salt in, you can see those little crystals, and if you add too much salt, you'll even see new crystals form on the way out. So this is an equilibrium. There's a back and forth happening here. So here we go. We've got, for example, here's our silver chloride example again. This is the net ionic equation, but rewritten as an equilibrium between the solid precipitate and the silver and chlorine atoms. They are constantly in a state of flux. There are silver ions floating around the solution. There are little silvers here, and they're floating around, and they're doing their thing, and then every once in a while they're going to find a chlorine ion. I don't know why I'm spending so much time on this drawing, and they're going to find a chlorine ion and get stuck together and then float towards the bottom of the solution. And if they find enough of them, you might even see some precipitate forming on the bottom. And at the same time, at any given point, if the solution's at equilibrium, they could easily just as easily fall apart and go back into solution and float around and do something or other. Probably find themselves again. So we can also interpret this into a solubility product equation, or the same idea as what we did in our equilibrium. So that's what we're going to do. That's really it. So at a given temperature, the equilibrium law for the given reaction would be K equals, or in this case, we're going to call it, let's call it KEQ. And so we would write a KEQ, and we would put the concentration of A plus and the concentration of B minus, and we'd put it up to the powers of A and B. And then we would normally divide it by the reactant, right? The concentration of A, B, B. But do solids have changing concentrations? No. There's changing amounts of solid, but the concentration, the amount of atoms per volume for a solid is not changing. So a little bit hard to wrap your head around. In solids, we call the amount of matter per volume, we call that density. The density of the solid should not be changing, so the concentration of the solid can't change. That's one way to conceptualize it. So we're just going to get rid of it. It's a solid. Solid don't have concentrations. They are not really part of the phase. They're not in the aqueous phase. To calculate an equilibrium, we really have to be talking about things in the same state. All right, so here is what happens. You reduce it down, you get rid of that KEQ, and you call it KSP for solubility product. Does it mean anything different? No. Is it confusing that it's not KEQ? Probably, and it's really probably unnecessary. It's an unnecessary change, except that it does help remind you that you don't need a denominator. You don't need to divide by anything. So all you need to do is look at your chemicals. So if they give you calcium hydroxide, for example, calcium hydroxide, if we think of it as being a solid, and it could break apart, in this case, into a calcium 2+ ion. You can look at an ion chart for that if you need, or you can calculate it back from the reactant, from the charge balance inside the chemical, and you'll get this. And these are the only two, the products are the only two that matter, so they go into the numerator. And then, of course, our denominator here is 1. It's not changing. We get rid of it. And so our KSP will be, the solubility will be based on the concentration of calcium and the concentration of hydroxide in solution. So this really just means that for a certain amount of calcium and a certain amount of a hydroxide dissolved in a solution, you will get the formation of precipitate. How much precipitate? Difficult to calculate at this point, but you will definitely get one. And it also implies that there's only so much calcium and hydroxide that you can even put in a solution. Okay, I kind of skipped ahead on a couple of these. So if you want to go through the details here, we can take a lead 3PO4 and 2. We can treat that as our solid, get that chemical reaction up there. Make sure you do your calculations very carefully. You might need to go look up an ion chart if you're not comfortable with calculating it from the formula. If you aren't comfortable with calculating it from formula, maybe that's something you should review. I know that lead has only 2 oxidation states, +2 and +4. In this case, I also know that PO4 is usually 3-. I can't think of any examples where it's not. And so I look and I say, well, if PO4 was 3- and I have 2 leads, then that means that I have 2 PO4s. 2 PO4s times 3- is a total of -6 charge, because we have 2 of these. So we have total -6 charge, and then the lead, there's 3 of them. So how do I get to +6 to balance? Well, I have to give lead that +2. Hopefully that helps at all. Some students have some success with doing a little chart. They know that lead has a +2, and they know the PO4 is a -3, minus. So something like this, plus. And so if you you have to try to make a set of these. So I'm going to cheat a little bit for some speed here. I'm going to take a duplication here. And so I have 2 of these side by side. Go in and make these negatives a little bit more obvious. So we have the 3 negatives, 3-, And so to balance this out, I'm going to need to go 1, duplicate, 2, duplicate, and 3. So we can see that with 3 2+ leads, we can balance out 1, 2, another 2 charges from the lead, and another 2 charges balances out that -6 from the PO4. So that's one way of calculating things like that. All right, so we can then do all the old equilibrium calculations we did before, but now using concentrations that we are given for the ions of these various compounds. So here we are given the concentration of silver ions, so that's silver ions, that's the Ag+, at some value, and the concentration of chlorine ions, so that will be our Cl- at some value, and then we can calculate the Ksp from those values. And so there we go. We multiply the 2 numbers as they replace them in the equation, and we get our Ksp. So now here's our Ksp, final value. Here's another example with calcium fluoride. Watch out, in calcium fluoride we have CaF2. So that means that the reaction will form 1 calcium 2+ plus 2 fluorine minuses. And put our phase states here and our solid. Okay. So that 2 means that we get an exponent of 2 in our product, solubility product. Of course, if you were given the solubility of a compound, then you could even go back and work backwards to figure out how much you got in there. You could even use the amount of dissolved compound to figure out what the solubility product constant is. So here's a very interesting example. This example number 4. They give you the solubility of lead fluoride in grams per liter. This is because this is a very easy to measure method. You just take your little beaker, put some water in it, maybe put a liter of water or some known amount, and then place the whole thing on your scale. And then while it's on the scale, you can just sort of sprinkle in your a little jar of your sample here. Add that in, and until you see a precipitate form. And as you sprinkle that in, the weight will go up, and once you have sprinkled it in to the point where it stops dissolving, you'll know how many grams in that liter of water you were able to add by the amount of weight you increased it by. So this is what they did. They got grams per liter, so first things first, they need to convert that into a concentration we can use. So we can do that by multiplying by the mass mole ratio. So here is the number of mole. For 1 mole, we know the molar mass. I just calculated this roughly from 207 being lead and 19 being the fluorine. Added those masses together from my periodic table, and then did the multiplication, got this molarity. So this is moles per liter now because the grams have been canceled. Grams are gone. Take that moles per liter and realize that this must be the number of moles of lead, and then I actually get twice as many moles for fluorine because we know that lead fluoride must dissociate in solution into a single lead atom. So however many moles of lead I have the same number of moles of, or how many moles of lead fluoride I have the same number of moles of lead and fluorine, but we get 2 fluorines for every molecule, so we get twice the number of moles, and that means that the concentration is twice for the same volume. So here's our new setup. We have our KSP taken from our equation, so that's why we always want to write our equation out, and then we replace the concentrations inside that equation, and then calculate the new KSP value. Here's another example. If you have a KSP but you don't know anything else, then you do know at the very least that there must be some sort of ice-like dissociation, so some initial concentration, a change, and an equilibrium value. You take the change to be in terms of x. So we go from 0 to plus x for the magnesium. We have to go by the molar ratio for hydroxide, so we get 2 x's. Plug those back into our KSP equation, and we'll end up with a setup that looks like this. You can use your calculator here, or you can use a photo app or whatever. We can do a little division by 4, and then a cube root to figure out the total. And we should end up with something like this. This is now x. That means that this is the concentration of magnesium, because we know that the concentration of magnesium is equal to x. And the concentration of our OH, as I remember what we're doing, our concentration of our OH is 2x. So that will be a little bit more tricky to figure out, but it's just twice. So here's our 2 new concentrations. All right, last example, I believe, is calculating the solubility from the KSP. So do the exact same deal. We've actually got the exact same question here. We end up all the way down to x, and now what we want to do is think about which of these concentrations would be the same. If it's at this solubility point, then x here, this x, the number of moles of magnesium, had to have all come from the magnesium hydroxide. So this will also be the concentration of that magnesium hydroxide. And so the maximum amount of magnesium hydroxide you can actually dissolve in solution is to take your molarity multiply it by the molar mass ratio, mole mass ratio, and that will give you a final concentration in grams. So a gram conversion, really. And now there's lots of practice questions here, so good luck, and we'll talk to you soon.